I would like to welcome you to the session Paving the Way Toward Automated Driving with BMW Group. My name is Mark Newman. I'm a product owner for data engineering and automated driving at BMW Group. We built the necessary tooling and environment for the development and validation of automated driving systems. With me today is also Junji Tang. Junji is a principal consultant at AWS Professional Services. In this session, I would talk on how BMW Group uses data from its worldwide connected fleet of customer vehicles for the development and validation of automated driving systems. I'm going to explain the purpose for the data collection, give an example on how we analyze the data, and provide an overview on our pipeline on AWS. In the second part, Junji Tang from AWS will explore with you the AWS Autonomous Vehicle Data Lake reference architecture. You will learn how customers manage the challenge of ingesting, transforming, labeling, and cataloging massive amounts of data to develop automated driving systems by using Amazon EMR, Amazon S3, and Amazon SageMaker Ground Truth, amongst others. A rising number of vehicles by BMW Group are equipped with automated driving and safety systems. These vehicles possess an array of sensors to perceive their environment. Those sensors detect, for example, other vehicles, pedestrians, and road lanes. In the first lane, this environment perception serves as the most important input for the driver assistance and automated driving systems. But secondly, this environment data can be used off-board from the vehicle for analytics. With sufficient data at hand, we can gain a holistic understanding of driving situations. For gaining this understanding, we collect perception data and state information from the vehicles. But what is the data that we actually record? We collect the usage and availability of automated driving functions to understand, for example, customer usage behavior. We record positions of lane markings to understand, for example, lane change maneuvers. For detected vehicles, we record the relative position to the customer vehicle. We also collect heading, velocity, type, and dimensions. For the customer vehicle itself, which is recording the data, we also include information like velocity, acceleration, heading, and also the global position. And it is very important for BMW Group that this data collection is compliant with data privacy laws. We collect anonymized data without an option to identify the actual vehicle and customer. Also, we blur time information and limit data collection to certain road types. By doing this, individual vehicles cannot be identified, even when trying to find a driver by known driving routes. With the collected vehicle data, BMW Group can answer essential questions. This allows us to be more customer-oriented in our product offering. It enables us to monitor the quality of our products in use. It allows us to be more cost-efficient in our vehicle function development. And the collected data allows us to develop premium vehicle functions and, last but not least, safe and performant automated driving systems. One of the analysis goals is to understand edge cases, like safety critical situations. Those driving situations are very rare. This is the reason why we are collecting more than 1 billion kilometers of perception data from around the world. This allows us to analyze a significant number of edge cases. Here you are going to see a safety critical situation that we recorded. In the following video sequence, you are going to witness a near accident prevented by the BMW Emergency Steering Assistant. The simplistic visualization is using the actually collected data. Let's follow the black-colored customer vehicle in the bottom right corner. There is a grey vehicle in front of the BMW car. This grey vehicle brakes to avoid the collision. The BMW driver brakes and starts steering to the right, but avoiding the collisions requires harder steering. The emergency steering assistant helped the BMW driver and enforced steering to avoid the collision. Luckily, these situations are rare, but since we are collecting 1 billion kilometers of data, we can find a substantial number of edge cases to use them for the validation of automated driving systems. Now let's have a look on how we use the collected data for analytics with an example. In this example, we analyzed a certain type of driving scenario, the cut-in. A cut-in is a situation where a customer vehicle is driving straight on a lane and then another vehicle changes to the same lane in front of it. In the video you are seeing, the green vehicle is performing a cut-in from right to left onto the lane of the black-colored customer vehicle. It is a basic scenario which happens quite often. Automated driving systems need to detect cut-in maneuvers early. This prediction of cut-in maneuvers allows to maintain safety distance and driving comfort. For this analysis example, we considered just two parameters for each cut-in scenario. Firstly, the distance between the customer and the other vehicle. And secondly, their difference in velocity. We would like to understand the distribution of real-world cut-ins regarding those parameters. This distribution explains, for example, how close in distance cut-ins usually are. We identified a number of those cut-in scenarios in Europe. You see two plots. On the left-hand side, the plot shows the cut-ins from the left to the right. Each point in the graphs is a separate cut-in scenario. On the x-axis, the difference in velocity is shown. For example, slower vehicles are plotted with a negative value for velocity difference. On the y-axis, the distance to the cut-in is represented. And on the diagram to the right, the cut-ins from the right to the left lane are shown. It can be seen that vehicles cutting in from the left are usually faster than the customer vehicle. Most of the cut-in data points in the left diagram are plotted in the positive velocity difference area. Vehicles cutting in from the right are mostly slower than the customer vehicle. This is no big news, since in many European countries, overtaking on highways must be done on the left lane. But when we use the cut-in data to fit a distribution function, it gets more interesting. A distribution function represents the real-world probabilities for cut-in situations. With this distribution model, for example, we can generate numerous simulation scenarios to validate automated driving functions. And we also find outliers, like the circled one. This outlier situation requires a fast intervention by the customer vehicle to avoid the collision, since the other cutting-in vehicle is substantially slower but very close in distance. You can think of many more analytic use cases with the collected data. The cut-in analysis is just one of the more simple ones. It focuses on a specific simple driving situation. Let me just quickly show you a more complex example without going into much detail here. It is about gaining an understanding on the different types of scenarios that can occur. This can be approached in two ways. One approach, you have a fixed list of driving situations and are matching this with the collected data. This is what we not did. We did it the other way, shown here, using an unsupervised approach. In this unsupervised approach, we applied machine learning methods to cluster a large volume of collected drives into scenario categories. First, we used deep learning to find the ideal model to represent scenarios. We tried different things and came up with an autoencoder approach that learned the ideal representation of features for a driving situation. Imagine the input to the autoencoder as shown in the white small box to the very top right. This is a situation where the customer vehicle overtakes another vehicle quite fast. The encoded version of the driving situations form points in multidimensional space. Each situation represents one dot in the diagram. Then we applied unsupervised learning to cluster the scenarios into categories. Unsupervised, without a list of scenarios. You can see the differently colored clusters of situation data points in the diagram. To enable analytics, as for the Cutin scenarios, a data preparation pipeline is needed. Our pipeline runs on AWS. Customer fleet data is received by our Cloud Data Hub. The Cloud Data Hub of BMW Group provides our enterprise data lake. There are numerous data assets that are filled by data flows from BMW Group IT systems. The Cloud Data Hub stores the received fleet data as Parquet files in S3. These files are simply split based on data volume. They contain events from many different vehicles. Thus, the first step in this pipeline is to separate the fleet event data by drive. This step is called ingestion. The result of this step is having the timely ordered signal values of each drive for each vehicle as a separate file in a S3 bucket. Ingestion itself is split into sub-steps. Let's look at the first of those sub-steps. First, we collect the file paths to all input Parquet files for the next scheduled batch run. When a new event file is added to the S3 bucket, then we add this file path to a queue. Secondly, we partition the new input files into separate drives. This is implemented in Scala as a Spark application, which is run in EMR. Scheduling is implemented via a triggering lambda. For starting up the EMR cluster and orchestrating the Spark jobs, we use step functions. The Spark driver retrieves the event files to be processed from SQS. The Spark executors then read the event files and write the events from each drive to a separate partition as new Parquet files. We call these the incomplete drives, since we did not yet determine which of the drives are finished. Since we are reading the vehicle events anyway, we store the latest event timestamp for each vehicle drive in DynamoDB. We need this information in the follow-up step to determine the actual completed drives. We run the full data preparation pipeline in longer batches, currently scheduled every 8 hours. This gave us the opportunity to use spot instances, since we are flexible on our batch scheduling. We use spot instances for the task nodes in the EMR cluster. This allows us to save additional costs. In the next substep of the ingestion, the step function workflow is launched in the next Spark application. This Spark job is called Completeness Checker. The Completeness Checker finds completed drives. There we retrieve the IDs of those drives from DynamoDB whose last seen event is old enough to conclude that the drive has ended. Those drives are loaded by the Spark executors and are written as timely ordered data in new Parquet files. Also, if there's a larger gap in the drive data, then the drive data is split into separate completed drives. As a result, we have complete, timely ordered data, but the data still is partly binary encoded and the different signals are not time synchronized. This makes it very hard to use the data for follow-up analytics. This is why we run the reference data generation in the next step. I would not go into details here, but mainly this step is again using multiple Spark transformations in order to produce timely synchronized clean data for analytics. Binary data like the attributes of detected vehicles is decoded. Signals with different frequency is timely synchronized. For example, the global position of the customer vehicle is sent much less frequent than the odometry information. Also, and this is one of the more complex tasks, noise in the data is removed. Since we are now processing the complete drive, we can, for example, remove so-called ghost objects. These are false positive vehicle detections that occur for a very short time and then disappear. The resulting reference data uses a wide table schema with protobuf serialization for nested data, like the detected vehicles and their attributes. This reference data is more suited for analytic follow-up jobs and also manual explorative analysis. Now in step 3, we can automatically detect relevant driving situations. We call the core application of this step auto-labeling. A Spark application reads the reference data and runs multiple auto-labelers. The result of this auto-labeling is a set of labeled driving intervals. For example, an auto-labeler finds all Cutin scenarios in drive intervals. These automatically produced interval labels are then stored as scene intervals in S3. To allow searching on those intervals, we can merge timely overlapping intervals, for example, Cutin scenario and night drives. Then the merged labels are moved to an Elasticsearch instance to allow ad hoc searches. Step 4 is called derived distributions. On the one hand, using the found scene intervals, the scenario type distributions can be created. These describe how often a certain scenario type occurs. On the other hand, when we need scenario parameter distributions, we can run a Spark job in EMR reading reference data to create a distribution model for the parameters of a scenario type. We have seen how this could look for Cutin scenarios before in this presentation. In the last step, number 5, we do the general analytics enabling. For this, we provide the prepared drive reference data and found scene intervals for a broad audience of analysts. To do this, we will move and transform the data into the Cloud Data Hub's AWS account. For this, using GlueJobs is the right tool. Analysts can then use Athena to query the provided so-called semantic layer in S3. The pipeline I explained was and is being built by BMW Group's own data engineers together with a team of solution architects and developers from AWS Professional Services. Through this partnership, we learned a lot and could together optimize our early architecture ideas and leverage a lot of optimization potential to save infrastructure costs and build a leaner solution. So thank you for this. Now I would like to hand over to Junji from AWS. Junji is leading the AWS team working with BMW Group on the pipeline. Junji will broaden your vision by exploring the reference architecture for an autonomous vehicle data lake with you.
Thanks, Mark. Let's take a step back and look at the flywheel shows all the steps for ADAS and ADS workflow. We divide it into 4 areas. All the steps are not serial as we see many complex interactions between the various steps. We begin with the bottom left, data acquisition and ingest. Test vehicle will produce 20 to 100 terabytes per day, typically in a data logger with removable media. This data could be locally processed and transferred to AWS using Direct Connect. We go to top left, processing and analytics. Data will be decoded from binary code. Low-quality data will be archived or deleted. Metadata will be extracted, and a unified data catalog will be created. Analytics could be scene detection and statistic calculations, like the BMW Group's example before. Now we go to top right, labeling. To achieve high quality and low cost for the labeling workflow, vendor could combine automated labeling and human labelers. Amazon SageMaker ground truth could save up to 70% to leverage both. Model training is typically GPU bonded and needs large set of data of edge and core use cases. Simulation and validation is typically CPU bonded. Software in the loop, hardware in the loop, resimulation are common terms that make up these workloads. We end with bottom right orchestration and deployment. End-to-end CI/CD pipelines for the whole workflow. Deployment could be OTA or hardware replacement. We talked to different customers and our partners, and we found out 4 main challenges to build an autonomous vehicle data lake. So the first one is the storage. The test fleet could produce 200 to 600 petabytes per year. Data includes video, radar, and LiDAR information. Some OEMs and the Tier 1 told us that their on-prem data center couldn't store so many data. The second challenge is actually to build a scalable and stable processing pipeline. Vendors have globally distributed test fleets to collect high variety of driving conditions. How to deploy this data processing pipeline in different regions become a real challenge. The main success factor of BMW Group's project is to build a scalable data pipeline in weeks instead of months. The third challenge is standard-based search analytics. Data at your fingertips is the slogan of the Cloud Data Hub in BMW Group. We had a reinvent session last year and this year also. How to find a scenario that you need in the 1 billion kilometers is one of the key requirements in the BMW Group's project. High performance and throughput and low latency is the last challenge. High performance throughput is a must-have for the simulation and validation workload. P4D instances are powered by the latest NVIDIA 800 Tensor GPU. The virtual cluster of P4D instances could provide petabit scale non-blocking networking. So S3 is the foundation of AV Data Lake. It has 11 nines of durability, high availability, and scalability. It has the best security, compliance, and audit capabilities. It provides object-level controls. S3 has high performance and can be massively parallel and scalable. It has up to several hundreds of gigabytes per second without provisioning. S3 provides cost-effective storage classes with intelligent tiering. One key principle of Data Lake is to separate storage and compute and scale both individually. You can use Athena EMR or Redshift to access S3 through lake formation. Lake formation enables you to build a data lake from months to weeks and provide column-based access, which is quite common in enterprise customers. Here's a few customer references of AWS autonomous vehicles. Toyota Research Institute accelerates safe automated driving with deep learning at a global scale on AWS. They use EC2 P3 instances to reduce the train time by 75%. Too Simple mentioned that running the safety tests and the simulation will take weeks each time new code is rolled out. They use EC2 P3 instances. The test can be completed in a matter of hours. We talked to all the customers and the partners, and we defined the reference architecture for AV data lakes, especially for MDF4 and ROSBAC-based pipelines. We divided into 10 steps, and we will walk you through all the 10 steps. The first step is ingest data from autonomous fleet. Vendors test fleet can use data logger to collect data. There are a few partner solutions on the market. Each vehicle could provide 20 to 100 terabytes per day. The test fleet could be globally distributed. In each copy station, you could install AWS Outpost to process the data locally. Data could be installed in S3. Customers use EMR or EKS to check the data quality and completeness. Incomplete data could be deleted to save the cost. The data could be replicated to AWS using data sync between NAS and S3. The second step is to ingest vehicle telemetrics data in real time. Telemetric data could be CAN data, GPS locations, ADAS system output, road conditions metadata derived from cameras. Telemetrics data can be collected by IoT Greengrass in the car. AWS IoT SDK is the lightweight solution to collect and ingest data. The telemetry data can be ingested via IoT Core into Kinesis firehose. This data will be combined with the sensor data captured from the data logger process in step 1 and stored in S3. Step 3 is remove low-quality data. Typical tasks could be drive completeness check, pass the recording format, ROSBAC or MDF4, decoding signals, filtering inconsistent data. EMR Launch is an open-source framework developed by AWS Professional Services team. It simplifies the defining, deploying, managing, and using Amazon EMR clusters. In one of our customers, we optimize the code and use spot instances. The process time went down from 9 hours to 3 hours, and we saved the cost by 82%. Step 4 is to schedule the ETL jobs using Apache Airflow. For one customer, we deploy the Airflow on AWS Fargate on ECS to process the radar and video data in MDF4 format. It provides 5 times capacity and reduces the cost by 90%. We are writing a blog and open source the code very soon. Step 5 is enrich weather data and map information. The HD map information will help the safety function developers to understand the scenario with more details. Step 6 is to extract metadata into Amazon DynamoDB and Amazon Elasticsearch. Using the BMW Group sample with 1 billion collected kilometers, others developers want to find the scenario quickly and see the visualization. A data catalog is built to create searchable metadata that includes speed, turning angles, location, as well as simple and complex semantic descriptions such as high velocity, left turn, or pedestrian. Open scenario is a common standard for scenario description. Step 7 is data lineage in Amazon Neptune and Google Data Catalog. Google Data Catalog provides a centralized metadata catalog for different services like Athena and Redshift. Amazon Neptune is a fully managed graph database. Customers use Amazon Neptune to track the dependencies between file version, and scenario and simulation artifacts. Step 8 is process drive data and perform deep signal validation. Only a subset of the signals from the ROSBAC or MDF4 files will be extracted for KPI calculation and aggregation. You can use EKS for the KPI or statistical calculation. Step 9 is automated labeling using SageMaker Ground Truth. Labeling is hard. Ground Truth offers automatic data labeling, which uses a machine learning model to label your data. You can create customer workflows for data labeling that leverage human workers from Amazon Mechanical Turk, the AWS Partner Network, or your own private workforce to improve the automated labeling accuracy. It now supports 3D point cloud labeling for task types like object detection, object tracking, and semantic segmentation. The last step is to provide data access using AppSync. AppSync is a managed service that uses GraphQL to make it easy for applications to get data from a range of data sources such as Amazon DynamoDB, Amazon Elasticsearch, and AWS Lambda. In the BMW Group sample, AWS developer can search scenario in DynamoDB and Elasticsearch use the AppSync interface. We had a reinvent session about AppSync in BMW Group's Data Lake last year. If you're interested, you can find it in YouTube. So what are the other aspects to consider? So the first one is data encryption and anonymization. Some other use cases include sensitive or personal information. Vehicle identification numbers and personal faces can be recognized in Amazon Recognition. We could blur it. There is an AWS block for the usage in Toyota. Another aspect is to exchange data with partners. AWS Data Exchange is a service that makes it easier for AWS customers to securely exchange file-based datasets in the AWS cloud. Thanks for joining our session today. Please join other automotive sessions in reInvent, which includes AUT 201, transforming the automotive industry with the industrial cloud, AUT 301, Alexa Charge My Car, test drive the Accenture EV roaming platform, AUT 303, reimagining mobility with Toyota Connected. Thank you.